Okay, so now we're going to talk about the divergence between two submanifolds. So previously, of course, we started talking about the divergence between 2 points. Then we extended this to the divergence between 1 point and one submanifold. And so the next natural generalization is to consider the divergence between 2 submanifolds. Right? So imagine you have one submanifold and another submanifold. Let's call that K and S. And it's like, if you recall, it's like when we had talked about the issue of divergence between a point and a submanifold, we were also interested in finding the point, it's like on the submanifold, where the divergence from, it's like the original point, it's like to that point in the submanifold was as small as possible, right? So the natural question to ask, it's like when you talk about the divergence between two submanifolds, is also whether or not you can find a pair of points, one in the first submanifold and the other one in the second submanifold, such that the divergence between those 2 points is equal to the divergence between the two submanifolds, right? So it's the arg minimizer or infimum, it's like of that thing. Okay, so when you have two submanifolds, K and S in a dually flat manifold M, submanifolds. So let's just call it divergence between K and S, right? And that's just the infimum over so it's the infimum over, say, P in K, Q in S of the divergence between P and Q. And then I'm going to think of this as equal to the divergence between a P tilde and Q tilde, where P tilde and Q tilde are the arc infimum, it's like of this, all right? So the 2 points P hat in K and Q hat, Q tilde, it's like, sorry, in S, right, are the closest pair between K and S. Okay, so that's what we mean. Okay, so you can ask, well, how do you go about it? It's like trying to figure out, it's like this pair of points P tilde and Q tilde, all right? So to obtain this pair of points, P tilde and Q tilde, right? One possible way of trying to do this is to do what is called a alternating minimization, alternating projection type method. Okay, so what you basically do is you start with 1 point, it's like on the manifold. So I start with Q0, it's like on the manifold S. I can do this geodesic projection, it's like which we had talked about previously, of the point Q0, it's like onto the manifold K. So let's call that P0, right? And then once you've done that, now I can do a projection of the point P0, it's like onto S, okay? gives me Q1. And then given Q1, I could project back to P1 on K. Given P1, I can project back to Q2 on S. All right? So the hope is that, if this projection converges, right, then you would have a pair of points which is at least a local minimizer of this divergence between two points on this pair of manifolds. Okay. So, and the reason why this ends up working reasonably well is because what you can check is that there's a monotonicity property, which is to say that the distance, it's like between sort of, it's like the last pair of points, right, is going to be monotonically non-increasing. Okay. So you can observe that such a method has the property that the divergence, it's like between P, say K minus 1 to QK is greater than equal to the divergence from PK to QK, which is greater than equal to the divergence from PK to QK plus 1. Okay? So that sequence, that distance is monotonically non-increasing. Okay. So the procedure sort of converges. Then it turns out that it is unique when S is flat and K is dually flat. Otherwise, the limiting point, it's like from this iteration, may not be unique, right? So it basically may depend on the initial guess. Okay, so later it's like what's going to happen is that these notions of projections and dual projections are going to be named in a particular way. So let me just sort of briefly say what they are. It's again, and why it is that they're called what they're called. So let me just state this as a remark. So in sort of the later part of the book, right, geodesic projection is called E projection, corresponding to the exponential family. So this is exponential projection. And dual geodesic projection is called M projection. Which is called the mixture projection. And that's because the exponential families and the mixture families are going to be dual. It's like in some very, very natural sense along the lines of what we've discussed before, okay? And so as you might expect, it's like this alternating projection method has a combination of primal projections onto one surface and dual projections on the other, and you alternate between them. So this procedure for it's like alternating projection. It's like in order to find a pair of points, it's like which achieve, it's like the minimum divergence between two submanifolds is going to be called the EM projection algorithm or the EM algorithm. So the sort of alternating sort of primal dual sort of projection algorithm is called the EM algorithm. All right. Okay, so that's basically what I wanted to say about this. All right, and again, the intuition behind this is quite straightforward. It builds upon it's like what we've discussed in terms of projections of a point that's like onto it's a submanifold. And so again, you start with an initial point on one of the manifolds, you do a projection, it's like onto the other one. With that point, you project back onto the first manifold, and you keep doing this. And because of this this monotonically sort of non-increasing property, it's like of this sort of sequence of pairs, right? In terms of the divergence, right? The method is going to converge. And then because of the fact that these families of probability measures, it's like the exponential family and the mixture families are related. It's like in a very, very natural way. It's like through the duality. It's like which we've been discussing, right? The geodesic projection is referred to as the E projection, and the dual geodesic projection is referred to as the M projection. These spaces are dual. There's some sort of duality, it's like between these two projections, and then this ultimating sort of primal dual projection algorithm is called the EM algorithm. All right, so let me just stop here for now.